Hello everyone, my name is Mridu Das. My roll number is MEB 17070 and I am going to discuss some questions about compressible flow. So the first question is a hydraulic turbine is designed to produce 26.845 megawatt at 95 rpm under 15.24 feet of head. Laboratory facilities are available to provide 4.572 feet of head and to absorb 37.285 kilowatt from the model turbine. So we have to determine A. The appropriate model test and scale ratio, and B. Volume flow rate, assuming a model efficiency of 86%. Now it is given that for prototype speed N1 is equal to 95 rpm to produce power P1 at 26.845 megawatt, that is 26.845 into 10 to the power 3 kilowatt, and head H1 is equal to 15.24 feet. Now 1 foot is equal to 0.305 meter, therefore head H1 is equal to 15.24 into 0.305 is equal to 4.6482 meter. So we have to make a prototype in the laboratory. Now according to laboratory conditions, to make the prototype, H2 head is given 4.572 feet, which is equal to 1.39446 meter, and power P2 is given 37.285. Now since Nu speed unit speed is constant for both the conditions, therefore Nu, that is unit speed, is equal to N2 by root H2, which is equal to N2 is equal to 44.063 into root over 1.39446, which is equal to 52.032 rpm. Now using expression for head coefficient, Ch is equal to N1 square D1 square by H1, which is equal to N2 square D2 square by H2 square. Now by doing the calculation, we found D1 by D2 is equal to 0.99. The model test speed N2 is equal to 52.092 rpm. Now scale ratio means respect to the main turbine how much scale it will be. The model efficiency is 86% as given in the question. Now model efficiency is equal to 86% and H0 is equal to H2 by 1000, that is the efficiency is 0.86. Now using the formula of efficiency, which is P2 by rho G Q2H. Now using the formula, we found the flow rate Q2 is equal to 3.16 meter cube per second. Therefore flow rate for test model under laboratory conditions is 3.16 meter cube per second. Moving on to the second question. Second question is condition at the inlet to the nozzle of a Pelton wheel are P is equal to 48.2633 bar and V is equal to 24.14 km per hour. The jet diameter is D is equal to 19.05 centimeter diameter, which is the diameter, and the nozzle loss coefficient is 0.04. The wheel diameter is D, capital D, is equal to 2.44 meter. At this operating condition, the hydraulic efficiency is 0.86. So we have to calculate number A, the power output, number B, the normal operating speed, C, the approximate runaway speed, D, the torque at normal operating speed, E, the approximate torque at zero speed. Now, we use Bernoulli equation, that is energy at inlet is equal to energy at outlet. K is the loss coefficient. To balance the equation, we use K, the loss coefficient. We have to consider all the energies. Then by using this formula, P1 by rho g plus V1 square by 2g, which is equal to Vj square by 2g plus K Vj square by 2g. Now by doing the calculation, we found out that Vj is equal to 96.45 meter per second. We know that flow rate is volume into area, so Q is equal to Aj into Vj, and Aj is equal to pi by 4 d square, and d is the diameter of the nozzle. So by doing the calculation, we found Q is equal to 2.73 meter cube per second. For head, the formula is P1 by rho g plus V1 square by 2g. Energy difference will be the same, so by doing the calculation, we found head is equal to 494.76 meter. Now the formula of power is P rho QGH. We multiplied efficiency to get the actual power by actual power, so the formula is rho QGH into efficiency. So by doing the calculation, we found out output power 11.39 megawatt. For normal operating speed, the velocity is 0.46 Vj. We know that U is equal to pi nd by 60, as we have to find in RPM. So using the formula, we get N is equal to 347.39 RPM. Now, runaway happens when U is equal to Vj, which is equal to 96.45 meter per second. As the previous formula, we just have to use Vj in U. So by doing the calculation, we found N is equal to 755.32 RPM. The formula of torque is efficiency into rho Q d by 2 V1 minus U 1 plus cos theta. Now in Pelton turbine, inlet angle is perpendicular to the blade, so we can write as efficiency into rho Q d by 2 into V1 minus U. So we get torque by calculation as 349.142 into 10 to the power 3 Newton meter. Now when the speed is 0, that is U is equal to 0, we will use the same formula, but U will be 0. So torque at 0 speed is 646.473 into 10 to the power 3 Newton meter. Now the next question is, the reaction turbine at Niagara Falls are of the Francis type. The impeller outside diameter is 4.5 meter. Each turbine produces 54 megawatt at 107 RPM with 93.8% efficiency, 165 Calculate the specific speed of these units. Evaluate the volume flow rate to each turbine. Estimate the penstock size if it is 400 meter long and the net head is 83% of the gross head. Assume suitable data if necessary. Now, the outside diameter is 4.5 meter. Turbine produces 54 megawatt at 107 rpm. Head is given as 65 meter and X efficiency is 0.938. For specific speed, the formula is Np to the power half by H to the power 5 by 4, and by doing the calculation we get the specific speed 134.722 rpm. To find the flow rate, we use the formula Q is equal to P by X rho GH. We know the value of P, X, which is the efficiency, rho, which is 1000, G 9.81, and H 65. So we get the value of flow rate 90.28 meter cube per second. Now net height H is equal to 0.83 H naught. H is equal to 65 is equal to 0.83 H naught. Therefore H naught is equal to 78.312 meter. Now we use the formula H cross is equal to H net plus HF. Then by the calculation we get HF is equal to 13.312 meter. Now the formula of HF is FLQ square by 12D to the power 5. L is equal to 400 meter is given in the question. Q we got from the calculation, and F from Moody's chart. We get the value of D, which is 3.896 meter. Now the fourth question. A propeller turbine has been designed to develop 22,000 kilowatt under a head of 20 meter wheels turning 150 revolutions per minute. The relevant data is hydraulic efficiency is 95%, overall efficiency is 88%, outer diameter is 4.5 meter and diameter of the hub is 2 meter. There are no vane angles at the hub and at the outer periphery. Assume that the turbine discharges without wheel at the exit. In the propeller turbine, given power developed is 22,000 kilowatt under a head of 20 meter. Power P is 22,000 kilowatt, head H is equal to 20 meter. Overall efficiency is 88%. Outer diameter is 4.5 meter. Hydraulic efficiency is 95%, and diameter of the hub is 2 meter. We have to find the runner vane angle at the hub and the outer periphery, means blade inlet angle and outlet angle. We have to assume the turbine discharges without wheel exit. Now, as given in the velocity diagram, VW2 is the wheel velocity outlet, VW1 is the wheel velocity at inlet, U1 is the mean blade speed, V1 is the velocity of jet at inlet, Vf1 is the flow velocity at inlet. We have to find the angle theta, that is the blade angle for inlet and outlet. Now, as Vw1 is equal to 0, so V2 is equal to U2 as shown in the diagram. Now the formula of hydraulic efficiency is mu H is equal to Vw1 U1 by GH. Now we know hydraulic efficiency is 0.96, U1 is equal to 150 rpm. Mean velocity at 20 meter is given, and then by doing calculation we found Vw1 which is 5.26 meter per second. Propeller turbine Vf1 is equal to Vf2 is the property of propeller turbine. Now Vf1 or Vf2 by U2 is equal to 10 theta 10 phi. Sorry. Now overall efficiency. In this formula we know that the output, which is 22,000 kilowatt. Now to get 22,000 kilowatt of output, how much input will be needed? So by using the formula of overall efficiency, we got the input of 25,000 kilowatt. Now the input power is given by rho GQH. It is in kilowatts, so it is divided by 1000. Now we know the value of rho GH, so we will get the flow rate Q, which is 127 and 127.55 meter cube per second. We know that Q, which is flow rate, is equal to velocity into area. We know that the velocity Vf2 is equal to Vf1, same for propeller turbine. The formula is rho GQ into H by 1000. And after doing calculation, we got Vf2 is equal to 9.99 meter per second. Now from this we can find 10 pi from the triangle. We got U2 by using the formula pi d naught n by 60. Then by doing the calculation we got phi is equal to 15.74 degree, which is runner vane angle at outlet. And for the inlet we can write the formula 10 phi, which is equal to Vf1 by Vw1 minus U1. We got U1 by using the formula given, which is equal to pi dh n by 60. dh is the diameter of the hub or the inner diameter, and by doing the calculation we found the runner vane angle at inlet theta is equal to 18.2 degree, and we found U1 by using the formula U1 is equal to pi dh n by 60. Thank you.